Yeah, good morning, sir. Am I audible?
Hello. 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 A lot of disturbance. Hello. 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 I welcome all the participants to second day session. Hello. Yeah. Please, Hawaldar, Jagdish Hawaldar, please mute your microphone.
Yeah, thank you. Now I welcome all the participants to second day session. The presenter is OMP Hawaldar, Dr. OmPSuthara. He is professor from Department of Mathematics, Malaviya National Institute of Technology, Jaipur, Rajasthan. He has completed his PhD in 2010. He is a JRF in 2006. Then he got a fellowship, Dr. D.S. Kothari postdoctoral fellowship. He was he was awarded as a best paper presenter in 56th Congress of Islam in 2011. He has got totally 9 years of teaching experience and 2 years of postdoctoral experience. Presently, he is working as assistant professor in MNIT Jaipur. Earlier, he served as served at NIT Jalandhar and VIT Vellore. His research area is linear and nonlinear stability analysis in thermal convection flows. He has published around 11 papers in international and national journals of repute. Now, with this small introduction, brief introduction, I'm handing over the session to Dr. OmPSuthara. Please
Yeah.
continue.
Thank you very much, sir.
Yeah,
I hope it is audible to everyone.
yeah.
And may I please request Jagdish Havaldar to mute his mic because it is still there. Noise is there. Okay.
Now, Jagdish Havaldar, please mute your microphone, please. Yeah,
Okay. Just as a confirmation, I hope the slides are visible to all of you.
yeah, it's visible.
Okay. So thank you, sir. Thank you, organizing. Thanks to entire organizing team for inviting me to share my work in this FDP. As sir has already told that my work is in the field of thermal convection, the convection that occurs due to temperature differences. So such a phenomena is actually observed in atmospheric convection. And today I'm going to share with you the idea of chaos in atmospheric convection. Chaos is a pretty famous word nowadays. A lot of people are working on that, and chaos and turbulence. That is what very famous in fluid dynamics. So I'll just tell you about the introduction of this. That how chaos was first observed in physical systems. Earlier mathematicians of even last century they had already realized that there can be systems which are chaotic, but they really did not have any experimental knowledge till that time. And then came one person who performed this experiment and performed the experiment in the sense he gave a theoretical proof that yes, chaos exists even in some natural processes as such of atmospheric convection. So first of all, what is atmospheric convection? It's a very simple idea that when we have sunlight over there and when it hits the ground temperature increases. Well, another confirmation I want is whether you can see the mouse or any pointing device over there. Can you see the mouse scrolling over there, or I have to speak like without any mouse? Because the pointer, I cannot see the pointer as such. Is it visible?
Pointer is not visible.
Okay. So I'll be telling in words only, I think, because as the pointer is not visible as such, I can see the pointer. This has happened with my earlier talk also. So I'll maybe next time I'll figure out something for this. Okay, so when the sunlight hits the ground, then ground gets heated up, and the air which is in immediate contact with the ground, as you can see in the picture, is actually gets heated up as well because it comes into contact with the ground, which is at a slightly higher temperature. As you go away from the ground, that means as you go at a height, then you can obviously see that the temperature will be lower over there. Well, obviously, there is some effect of radiation on the air, but that is not much compared to the heating from the ground. And hence, what will happen is that we will have hot air below near the ground, and when we'll have means heavy air on top of it. So this is not physically possible that you can have heavier stuff above the lighter stuff, particularly in fluids. So what happens is an overturning happens. That is what we call it. So these heavier particles which are above of the air or whatever gases, it has to come down under the action of gravity, because gravity is going to pull them down. And since they are coming down, obviously something has to take their place. That is what we have continuity in the fluids. So when heavier particles are coming down, the lighter particles will go up. So as you can see with the blue arrows here, that the cool air which is going to sink, actually it is going to come near to the ground, and the warm air is going to rise because it has to take the place of that cool air. And obviously it is, since it is lighter, then obviously it cannot be below the heavier fluid. This pattern forms a circle, as you can see over there, and this circle actually is a clockwise one. This is called one cell. The nearby cell will also be there, because this is going up. The nearby cell will be in the opposite direction, because if it is clockwise, then the next cell will be anti-clockwise, and that is how air flows, as you know. Means all of you almost know that this fact, even though we are not from meteorology, but we know that at the near the ground, if the air is flowing from north to south, then obviously at a height it has to flow from south to north. It has to be opposite, as you can see. So with this idea, Edward Lorenz was the guy who thought that how to model this. There was already a phenomena which was existing, which is similar to this, is called Rayleigh-Bénard convection, in which we consider the thermal convection in infinitely extended horizontal plates, in which one of the plate is heated up. That means the bottom plate which is heated up, and the upper one is cooled down. And when this is a similar phenomena to atmospheric convection we just discussed about. And what will happen when you heat up from the bottom? This is something which we do almost every day. When you want to heat up the water or you want to boil the milk, that is what we do. We heat it from the bottom, and the upper temperature obviously is less than the lower temperature. And when these buoyancy effects will dominate, that means when the density differences are sufficiently large, that means when you have lighter fluid below and means dense fluid above, then obviously overturning will happen. And as in a schematic, you can see that this is what we are talking about, that there is one layer which is hot and there is one layer which is cool. And if the fluid is in between, then obviously the particles which are near the hotter plate has to move up, and the particles which are near the cool plate has to come down under the action of gravity. So this is named as natural convection. There is no other force except the natural force, that is gravity over there. And these cells, as I said, that if one of the cell is clockwise, the next one is going to be counterclockwise or anti-clockwise. And such cells, that's why we consider the plates to be infinitely extended, so that we need not to talk about any boundary, means vertical boundary. Because of that, fluid motion will be hampered. Here there is no vertical boundaries, as you can see. We have only horizontal boundaries, and that's what we mean by infinitely extended horizontal plates. Here one more thing we have done is we assume that the motion is two-dimensional, as you can see. So if I take horizontal axis to be x-axis along the plates, and if I take vertical axis as z-axis, so here we have assumed symmetry in y-axis. And this symmetry is shown in the pic below this pic. As you can see, the lower pic, as you can see that in y direction things are considered exactly the same, whereas x and z direction are similar to the picture which is above. And here we start our mathematical stuff, that we have to write the governing equations for this motion. So one thing which we write, equation of state, that is almost always there: conservation of mass, conservation of momentum, and conservation of energy. Here for equation of state we make use of Bose-Einstein approximation, which is very simple, that we are all already talking about density variations over there.
Professor,
Yes, sir.
Professor, just a minute. Your slides are not moving at all. It is just in the first slide only.
Okay.
Yeah. Now it's okay, and it is not full screen. Just
Okay. Is it okay now? Full screen if I'm going, that
yeah,
is what
it's
you are saying, that
visible,
it is.
not an issue, but not in full screen mode, presenting mode.
Okay.
I think it is not in slideshow. This one.
Okay, then let me just share the screen itself instead of sharing a window.
You please click the play button. I think there.
One second.
Hello.
Okay, it is saying that I don't have permission to share the screen. So if you can change the permissions.
Yeah. You can present it, not a problem.
For the screen, it is saying that you cannot share the screen.
Yeah, do it. Then okay, you do it as you did in the earlier. Present now you can click. Hello.
Yes, sir.
Sir, please click present now and select the Windows and then the presentation.
Okay, now is it visible?
Yeah, one more. Yeah, visible.
Is it in full
Yeah,
screen mode now?
it's perfect now.
Okay.
Thank you.
So, yeah. So this is what we talked about atmospheric convection. Maybe if you did not see the slide, this is the slide in which we talked about how the convection takes place. Is that when you have heavier fluid over here and lighter fluid over here, which is near the ground. Why it is light? Because the ground was heated up, and whenever fluids heats up, its density decreases. So this becomes light, and obviously heavier fluid has to come down under the action of gravity. Light means lighter fluid cannot be below heavier fluid. And as we talked about Rayleigh Bernard geometry, is that when we have a hot plate at the which is heated from the bottom, and when you have a plate which is cooled from above, let us say, so this entire fluid layer is going to have the motion like what we have in atmospheric convection. But the fluid which is over here near the hot plate is going to be lighter, and the fluid near this cool plate is going to be heavier. So the heavier fluid has to come down and lighter fluid has to move up. And that is what we call as means convection, natural convection. And one more thing we talked about was the symmetry in y direction. So as you can see that these cells which you see over here are actually symmetric in y direction. So once there is a cell here, exactly the same thing has to happen for all values of y. That means there is a symmetry with respect to y axis. So x-axis was along the plate in this direction, and z is the vertical direction. So x is horizontal direction, z is vertical direction, and y is direction perpendicular to this plane on which we are talking about, or on which we have this schematic of this problem. And governing equation, as I said, that equation of state, we consider this Bosniak's approximation, which says that when we are considering this buoyancy differences, that means we are talking about variations in density. So Bosniak suggested that you can take different means changes in density uh, to be negligible in all the terms except when you are talking of buoyancy terms. Buoyancy term is the main term, which is rho times g. That is actually about the mass of the fluid. So even if there you take rho to be constant, then means you are not talking about convection. You will say that the density is not changing, whereas we are saying that density changes with temperature here. And why we are taking this assumption is that it will become very complicated if I take rho to be a function of temperature everywhere in the equation. As you can see that conservation of momentum equation, we have density here itself. So if this also taken as a function of temperature, then this problem becomes very difficult to handle. And that's why this assumption, which works very well with all the practical problems which are solved till date. Conservation of mass is the continuity equation. Conservation of energy is taken as our equation for convective motion. This is the convective term, the second term over here. If this is taken 0, then we have our usual heat diffusion equation or heat conduction equation. The boundary condition we assume here is that the velocity of the fluid is 0 at the boundaries, the two boundaries which we are considering, the lower one and the upper one. And the temperatures are prescribed here. Lower boundary temperature is constant throughout. For all values of x, it is T0, and for all values of x at z equals to d, it is T1. And the obvious thing is T0 is larger than T1 because we are heating from below. And we want to see that phenomena of atmospheric convection. So obviously, bottom surface temperature should be higher than the upper one. These are the symbols which are used here. Uh, so first of all, we talk about the basic state. This basic state, there is no convection. In this, we can assume that the fluid is not moving at all. That means the velocity is zero in the beginning. And if we make use of this fact that velocity is zero, and since it is the basic state, all the basic quantities are independent of time. In that case, from the governing equations, we get simple differential equation, ordinary differential equations, which can be solved under the conditions which we just prescribed for velocity and temperature. So these basic state solutions can easily be obtained for temperature, density, and hydrostatic pressure. Okay, so more interesting thing is what we are looking for is the state of perturbation. So here what we do is there is a very simple idea in hydrodynamic stability theory is that if you want to check stability of a system, what you are supposed to do is to give a small disturbance to the system. So if you introduce a disturbance to the system, if the system remains in its earlier condition, then we say that the system is stable. Whereas if it goes away from its earlier situation, then we say that the system is unstable. It is something like we talk about stability of even an individual. But if you want to see whether a person is stable or not, disturb him slightly, and you will really see that how they behave. So it is similar to that. So stable people under any such disturbances remain calm. So here the calmness means our basic conduction state. So if the system remains in this state after some period of time at least, then we say that the system is stable. So here we introduce some perturbations. As you can see that temperature, the basic state temperature was TB, and we introduce a small disturbance to this, that is T dash. Similarly, V dash and P dash are the disturbances to velocity and pressure. Now Bose equation can be rewritten in terms of T dash and the basic state temperature. Similarly, an important term which is over there, which we will mainly focus on, is the temperature advection term. It is the term of convection, as I told, V dot delta T. And this term includes this T naught minus T1 by D term, as you can see. This is the temperature gradient over there. This is the thing which causes the motion over there, starting from the steady state, that is velocity v is 0. So, and one more term, this is actually disturbed terms, b dash dot del, and this should be t dash. I'm sorry for the typo. This should be t dash. Now, when we make use of these quantities, which we have assumed that T is changed by TB plus T dash. So if we replace this in the quantities, we get equations in perturbed quantities. So all these are perturbed quantities over there, and the conditions given are uh, the usual one, V equals to T equals to 0. And this is one of the final thing which we have to do to get the equations in a nicer form, is to non-dimensionalize the equation. And non-dimensionalization is a very, very important part of any fluid dynamical problem. Why do we perform non-dimensionalization? Is to make it happen that whatever we do in a lab is exactly the same which happens at any scale. That means if you have a model of aeroplane in a lab, then it is exactly the same as an aeroplane which is over there outside flying in the sky. And that's why non-dimensionalization is a very, very important aspect. So here we non-dimensionalize the quantities, and after non-dimensionalization, we get two non-dimensional quantities over there, PR and RA. So these are non-dimensional parameters over there, and these parameters actually now governs the flow. So Prandtl number is well-known ratio between momentum and thermal diffusivity, and Rayleigh number is the ratio between thermal force and the viscous force. And this Rayleigh number talks about the stability, that when the thermal force is sufficiently large, that means thermal force will be in such an amount that it can create that buoyancy difference, and it will overtake the viscous force, then only the motion will start, because viscosity's nature is to inhibit the motion. That means motion should not be there. That is what viscosity tries in a fluid. Okay, the boundary conditions, again, depending on what kind of boundaries we are taking. On velocity, we can have either derivative of velocity to be 0 or second derivative of velocity to be 0, which refers to stress-free boundaries. And one more thing is periodic behavior we consider in the horizontal direction as it was depicted in the figure, that we take in x direction, that there are cells and they are periodic cells actually. So if we consider any one set of cells, that means two cells that will be repeated throughout, and that's why horizontally infinitely extended layers are considered. And here in this case, to make things very simple mathematically, we consider free boundaries, which are actually non-realistic, because at least ground is solid in atmospheric convection also, even though if we assume the upper layer to be free. But still, we consider non-realistic boundaries, that the boundary conditions are simpler to handle mathematically, and we can get solution in very simpler form. Here further, as I told you earlier, that we assume the symmetry in y direction, so we can introduce a stream function for the problem. So once you introduce the stream function, we get simplified equations, which are obviously partial differential equations in stream function and the temperature. So, and there are two parameters, as you can see. One is Prandtl number, and the other one is Rayleigh number, as introduced earlier. And here this J stands for Jacobian of functions, phi and then psi and del square psi and psi and t. Now, so these are the governing equations as derived, and the corresponding boundary condition, as we said, we are considering non-realistic boundary conditions. So second derivative of psi is 0. And this is temperature. Psi stands for something like velocity, though it is stream function, it gives velocity. Like earlier, we wrote the conditions in terms of velocity. Linear stability analysis is the first thing we perform to talk about the Rayleigh number. And because, as I said, Rayleigh number is the quantity which tells us that what will happen to the flow, whether it will be stable or unstable. So for this, we avoid all the nonlinear terms. First of all, we say that nonlinear terms are neglected here because a product of two small quantities is further very, very small. So these nonlinear terms which we have over here in terms of Jacobian, we neglect these two terms. And once you neglect these two terms, we have again PDEs, but to simplify this, we assume this normal mode analysis, which is again a consequence of assuming the periodicity in horizontal direction. So when you assume periodicity in horizontal direction, you can see that we have taken functions as sine AX and cos AX to represent psi and t over there. So this sine AX and cos AX, as we know, are periodic. Secondly, time dependence has been taken in terms of e raised to the power lambda t, as we generally do for ordinary differential equations also. And here lambda is the thing which will tell us about the stability. As you can see that if lambda is positive, then e raised to the power lambda t grows to infinity as t increases, or t goes to infinity. Whereas if lambda is negative, then you can see that as t grows, e raised to the power minus lambda t in that case is going to go to 0. That means this psi and t will be finite. It will not become infinite. Or in other words, you can say as t goes to infinity, they will become 0. The in-between condition will be that lambda equals to 0. If lambda equals to 0, then we can say that the flow is marginally stable. Either it is neither stable nor unstable. So that is the point from where stability and instability can be bifurcated. Here, this A which we have taken is called the wave number. By this only our cells are generated in x direction. So once we assume all that, then you can see that we end up with this capital D denotes d by dz. So we end up with ordinary differential equations here to handle. And again, the boundary conditions are the same. After non-dimensionalization, we have z equals to 0 and 1. We make use of Galerkin method here, which says that based on these boundary conditions, you have to choose the functions theta and psi. So choose functions such that they satisfy these boundary conditions, and then substitute in the equation and make the residual 0. So it is called weighted residual method. So here we substitute these psi and theta in the governing equations, and then we end up with this equation where for neutral stability, as I said, that if you want to check the bifurcation point, that whether it is stable or unstable, it is decided by lambda equals to 0. So this is marginal stability. So if you take lambda equals to 0, you can see that left hand side here will be 0. And to have A and B non-zero, we must have determinant of this matrix to be 0. Then only A and B can be non-zero. Otherwise, if A and B are 0, these are our earlier solutions, you can say basic state solution, when there are no disturbances. Remember that psi and theta represents the disturbances. So if A and B are 0, then these disturbances are obviously 0. So when we put this determinant of this matrix to be 0, we get the value of Rayleigh number, which is this. So it says that Rayleigh number, if larger than this, we will have convective motions. And if Rayleigh number is smaller than this, then we cannot have convective motions over there. Only conduction is possible in that case. These values for particular value of A, for which it is the least, is pi by root 2 for A, and the corresponding value of Rayleigh number is 657. That means if Rayleigh number is 657, then there will be no convection. And when Rayleigh number is 657.512, let us say, then the convective motion will start at that point. The realistic boundary conditions you can consider, well, again, the values can be obtained. It is done in the literature. Here we talk about now non-linearity, because that is the essence of chaos. Without non-linear terms, having chaos is impossible. So here we consider the non-linear terms also, and the same Galerkin expansion gives us these values. Here you can see that when you calculate this Jacobian, you get a term sine 2 pi z. And if we apply the Galerkin method and make the residual 0, since there is no sine 2 pi z in the both expansions we have assumed, one is sine pi z, second one is also sine pi z. So weighted residual method will make this term also 0. So to overcome this problem, Lawrence suggested that you take sine 2 pi z term also in one of these two, and it was taken in the temperature. So now temperature has two amplitudes. One amplitude is B1 and second amplitude is B2, whereas psi has one single amplitude, which is A. And now when I take this sine 2 pi z, the weighted residual method, when we will use, we will have sine 2 pi z times sine 2 pi z, and that term will be non-zero. But note that again, when I'll substitute these two in finding this Jacobian, we will even get a term which is sine 3 pi z. So this is a never-ending process. You can take infinitely many terms over here to keep on rectifying this problem. So it is suggested that, okay, you take two terms and see what happens, and the third term, if it adds any qualitative feature to the problem, then only you add. And that is what was derived by Salzman, that taking two terms are actually enough in this expansion, Galerkin expansion. So when we substitute this, these two Galerkin expansions, which we have assumed now in the problem, we end up with the simplified version of this system, which is obviously is a dynamical system. As you can see, that you have x derivative. This dot represents derivative with respect to time. So you have dx by dt, dy by dt, and d dash by dt given by these expressions. Here sigma is related to Prandtl number, and r is related to Rayleigh number. So these two are the free quantities here. As you can see, the first equation is obtained from momentum equation. It has no nonlinear terms here, as you can see. Whereas second and third equations are obtained from the energy equation, which was having a nonlinear term. So here, as it was shown, that when you calculate Jacobian for psi, it is always 0. So in the momentum equation, there is nonlinearity is 0, whereas nonlinearity is non-zero in the temperature equation, as you can see, or energy equation. So this is how we get nonlinear terms here, xz and bz. Another thing to note here is x, y, z are proportional to these a1. As you can see, x is proportional to a, y is proportional to b1, and z is proportional to b2. That means if I would have not taken this term, the second term here in Galerkin expansion, that means if I had taken b2 equals to 0, that means z equals to 0, and we would have got a linear problem, because if z equals to 0, then this nonlinear term becomes 0 over there, And since z equals to 0, we need not write this equation itself, third equation. So we get only two equations over there because we are not taking b2. So third equation will be missing, and we got only two equations which we have already got earlier in linear stability analysis. And that is why this term which has been taken, which is, you can say that a deviation from linearity, because if you take only b1 in temperature, that means you are just talking about linear problem. When we are taking b2, then we are talking about non-linear problem. So you can take this as a deviation from linearity. That brings into non-linearity of the problem. Okay. Well, simple observations in dynamical system is generally made that whatever derivative is over there, you can see that on the right hand side it should have a negative term, or a negative sign over there, so that with the time, as time increases, these quantities decreases, even if non-linearities are not there. So here comes the most interesting part of this entire thing. This was all mathematical analysis, which I have discussed with you. This is entire starting from governing equation to obtaining this dynamical system, which is called as the Lorentz model or Lorentz system. This is all simple mathematics, which is generally dealt in applied mathematics, making use of ideas of ODEs, PDEs, and the methods which are available over there with certain number of assumptions. Now comes the interesting part of this model, is that these computations were performed in 1963 by Edward Lorenz, and the computer at that time, which was used at MIT, Professor Lorenz was from MIT. So the computer that was used at that time was LGP30, as you can see in the image, and this was called Royal Precision LGP30. And you can see some of the interesting facts. This I have just included to take a break from rigorous mathematics to computations now. Is that the clock speed of this computer was 120 kilohertz. Well, I think most of us already know that nowadays we are talking about megahertz and gigahertz in our computers, not just computers, in our laptops actually, which you can carry anywhere. This computer nobody can carry anywhere. Once it is fixed, it's like, I think, very difficult. Weight was 360 kgs approximately, and the dimension, as you can see, is like more than a meter in length in one side. So, and approximate cost is $47,000. I don't know what was the cost of dollar at that time, but I think we are getting a laptop in 47,000 rupees now, which actually performs better than this computer. But whatever, this was just a representative image of this. Lorentz actually solved these equations, Lorentz model, which is a dynamical system, a system of three equations, and he observed something very interesting. Uh, this actually, his phrase is taken exactly from Lorentz paper, and he was telling that he went out to take a coffee during these computations when he was performing, and after he came back and he observed that what kind of results he is getting, and the same for the same initial data he had already performed the calculations. So when he again checked it, he found some abnormalities over there, and he said that there was very small errors which were over there in the initial data which was entered, and you can call them just like rounding of errors. So when there was a very small error in the initial data, he observed that the solutions were completely different. That means they were dominating the solution, and that is what we call as chaos. Chaos means your system is extremely sensitive to initial conditions which you are entering over there. So here I have made a small demonstration of this, what he observed over there. And well, in today's world, it is possible to demonstrate like this. Lawrence only printed these results. So here some parametric things I'll tell you that R is taken as 26.8 sigma. I have not written, it is taken at 8/3. And here there will be two lines. I'll start playing this. So here now you cannot see two lines, but there are two lines. One line is blue and one is orange. It is very difficult to differentiate between these two lines right now. So blue line is plotted by taking initial values for A to be 0, or X to be 0, Y to be 1, and Z to be 0. Whereas the second line, which is orange line, is taken with x equals to 0, y equals to 1.001, and z equals to 0. That means there is a very, very small difference between initial value of y, which was 1, and 1.001 in two different cases. Now you can see that there are two things. This is the evolution, time evolution of amplitude x here, as you can see. So t up to t equals to 20, you can see there is no significant difference. And now you can see that they are completely in different zones. Here observe that x values below this line are negative and above these lines are positive, which we have drawn here. This is the t-axis. So in a way you can say that since x is the amplitude of stream function, in other words, x is the amplitude of velocity. So if x is positive, that means velocity is from one direction to another direction, and let us just say that it is from north to south. So if I have observed initially temperature correctly, let us say the exact temperature was 1. If I observed it correctly, then you can see that at t equals to approximately 28, according to me, the temperature should have been the amplitude should have been negative. Whereas if you make a very, very small error in taking that initial value, that means if you take 1.001, as you can see around t equals to 28, well, it says that your velocity will be in completely opposite direction with a very high amplitude. So here you can see that the amplitude here is -7 approximately near t equals to 28, and here you can see it is completely dead opposite of that with a very large amplitude over there, which is approximately 10. So this phenomena is what is now known as chaos, that even though initial conditions were very, very close to each other, there was a very, very small error in taking the initial observation. But after some point of time, it is drastically different. And that is what weather is all about. We know that weather cannot be predicted for a larger duration. Weather generally is predicted for next 2 or 3 days. This is the reason, because it is very difficult to correctly observe the velocity of the air, at the same time temperature of the air. There may be small errors over there that may make your observation completely incorrect, even though you take a better model. Okay, so here you can see again I have plotted the same x value which we had seen earlier. So x amplitude, this is how it grows, and there is visible difference between these two. Similarly for y amplitude, which is the amplitude of temperature, linear you can say profile, and z is for deviation from linearity. And again you can see there is a slight change in that after some value of time t. So you can see after up to t equals to 20, everything is fine. Even though we made some error, still there is no problem up to t equals to 20. Here another thing is, that is what I was mentioning. These are the cells which are formed over there. When the air moves, let us say from the bottom, you can see that there are two counter rotating cells. That is what we call. And this cell is clockwise and this cell is anti-clockwise. But when we take t equals to 28, as I mentioned, since the amplitude is of different sign, so this cell which was supposed to be clockwise, as you can see that when you take small mistake in the initial data, then it will be completely different. So here these two images says that if you predicted that air will be flowing from north to south, it will be actually flowing from south to north. That means your observation or your conclusions are completely incorrect. Okay, there is one interesting phenomena which happens here with this is through equilibrium points, is that when we take the steady state of the system, that means we say that there is no change with respect to time now. That means derivative with respect to time are 0. So if I use that Lorentz model and if I take all the time derivatives to be 0, we get actually 3 points where there is no change with respect to time. And those 3 points are the origin, and there are 2 more points, as you can see. As you can see that the z value for these 2 points are exactly the same, and x and y value, they are in completely different octant, you can say. Here, if we do this in 3 dimension, it is a standard procedure to talk about the phase space. So you can see I have drawn 3 points. One point is this orange point, which is the origin, 0, 0, 0. So if the initial condition itself are 0, system is not going to move at all. As you know, it will be 0 only. So it will remain in this state. Whereas these 2 points are what we are calling as steady points. So if the system either starts from these points or if the system reaches these points, then there will be no more change with respect to time in the system. Okay, so we'll see now. This phase space is actually plotting x, y, z as a point. X is the amplitude of stream function. Y and z are amplitudes of temperature. So you can see how it progresses with time is that this is the nature of Lorentz system, that it keeps on rotating around these points, steady state points. And these steady state points actually works like attractors here. You can see that they are attracting this state of the system. This dot represents the state of the system. So you can see that it is one time in one octant. That means signs of the amplitudes are completely different in this octant. Whereas in this octant, signs of the amplitudes are positive. This side it is negative. So you can see that it keeps on switching between these two. And you can keep on doing this infinitely. So I'll just move it slightly faster. And you can see that when you keep on plotting this infinitely, it never reaches that steady state. It keeps on moving, and what we see is a butterfly kind of shape. And when this shape can be plotted actually in 2 dimension also. So that is what we mean by chaos, that we have deterministic behavior, but it is non-periodic. As you have seen that in the previous figure, if we see these patterns are not periodic at all. It is not that it is again and again repeating in the same plane. You can see that its trajectories keeps on changing. And even if you keep on solving, I have solved it for t equals to 40 or something. Even if you solve for 400, you will see that it is not periodic. It keeps on making new trajectories out there. Another thing with this system is that it is very sensitive to the initial conditions. Very, very small error in initial condition causes a huge difference between the solution which you should have obtained and you have obtained. So this is what is chaos about, and the famous thing uh, from this experiment is known as the butterfly effect, which says that the flap of a butterfly's wing in Brazil can set off a cascade of atmospheric events that weeks later, this is very important, weeks later means as we have seen that till some time your calculations are going to follow exactly the same as what happens, but after some time, that means weeks later, spurs the formation of a tornado in Texas. That means it may be at completely different places as well. It can happen, and flap of a butterfly's wing is what we are calling as rounding of errors. If very, very small error is there in your initial condition, and you have a tornado over there just by a flap of a butterfly's wing, this can be taken as positive statement also, that your all efforts are very, very important. Even it can be a very small effort, just like a flap of a butterfly's wing. Okay, this demonstration I'll skip. It is more or less the same. These are the phase planes. As you can, I have shown you already that this is the beautiful butterfly, and this can be projected on different planes to get these phase planes in two variables. This is in XY, this is in XZ, and this is in YZ. So here, the final remarks of this talk is that when you have chaos over there, such systems cannot be predicted, and the prediction will be true only for a limited period of time. So weather is a chaotic system, which can be predicted only for a few days in advance. And chaos actually means that your system is very, very sensitive to initial conditions. And it actually, this experiment really cleared all the doubts which were there about reality of chaos, because chaos was told by mathematicians that it exists, but nobody could prove that it really exists in real world. So this was the first computation. And now this system, a Marcus Lorentz system, is pretty very interesting. There was a physics faculty in MIT. Lawrence faced a lot of objections on his research that chaos exists. and the people said, okay, no, this atmospheric convection model is incorrect. That is what they say, and started doubting all the results. Then there was a friend of Lawrence, Malkus, Professor Malkus, and Professor Howard. They actually made a water wheel, which actually gives you Lorentz system when you write the governing equation for this. So imagine going other way around. We generally in fluid dynamics, we think about a system and write the governing equation. Here there was a governing equation, system of governing equation, and they made a model out of it. So this is something really out of the world. And actually they made this water wheel and proved that Lorentz model actually can be even experimentally realized. Okay, I'll not discuss about this. And there's one more thing. Till the time you ask some questions, this is a nice demonstration that chaos happens in other systems also, a double pendulum. So here these initial angles are there, as you can see from the vertical. 120 and 123 is taken so that you can see the difference very, very clearly. So there is a very small difference between the initial angle, but still, as you will see, that the trajectories are completely different. I'm sorry. So first one is at angle 120 and this is at angle 123. As you can see that they are behaving in completely different way. So this is again an example of chaos. So chaos happens in double pendulum as well. Okay, with this, some references which I used. Any questions are most welcome.
Thank you, Om, Professor Om.
Yes, sir. Thank you, sir.
Participants, if you have got any questions, you can ask now. I ask him to wait for, because he has got classes now. He cannot wait for longer time. Another 2 minutes we can share with him. We can spare with him. If anybody is having any doubts, you can ask now, or you can post it to me in the chat box. I'll send those questions to him. I'll get the answer for you.
Yes.
Any questions from the participants? You can unmute and you can ask now also. I'm hearing some voice there. Anybody? No. Share their opinion. Hello. Okay, I think there are no questions since he has got the class at 11 a.m. I think I'll ask him to wind up. Thank you, Dr. Om. It
Thank
was
you
a
very much,
very
sir.
nice, very nice pictures you have shown. It was quite interesting one. I hope people
Thank you,
have
sir. Thank you
followed
very
your
much.
lecture and they'll come out with more good ideas with new ideas, and they might share it with you. Thank
Yeah,
you,
sure.
Om.
Thank you very much, sir.
Thank
Thank
you,
you to all the
participants. Yeah,
participants.
yeah.
Okay, thank you, sir.
Okay. I just want to share a few things regarding the next session. Dr. S.K. Vama is not well, it seems, so not turning up. He has not turned up. So next session will not be there. From 11 to till the session will not be there. The next session starts with the afternoon session starts at 2 o'clock, 2:30. Please join us. for 2:30 session. Again, the topic is chaotic dynamics. It is chaotic hydrodynamics by Dr. Kanyasi from University of Tarapacá, Chile. So we shall join at 2:30 session. Thanks. We'll end the session now.